concrete deck, we looked at specifically the frequencies, what the TL is at frequencies for an average concrete deck. And again, we found it was slightly too high. And also the rooftop mechanical noise, which was, very loud on the roof, wasn't picked up down below. So we ended up with the idea that we ended up with the vibration path, which is that the vibration from the panels transmits down into the structure and then causes the concrete metal deck to basically act as a speaker, generating vibration, filling the space below. And then we looked at, other ways that sound could be created, for noise and vibration. So first is basically whistling, where, there could be whole tone, which we struck out, Helmholtz cavity, which we also struck out because there's no cavity. And then Aeolian, like Golden Gate Bridge, again, didn't really match. So we went with a more of Reed hypothesis, which in this case, you have metal, or it could be something else, but, vibrating, and in a fairly narrow space, it creates a noise. Think grass whistle or think harmonica, something like that. So basically, there was an air cavity and vibration for that. Also, one thing to note is that the Bay Area is special. So this is the daily wind pattern at the place. So 3 to 5 p.m. each day, there are wind gusts up to 15 miles an hour in a very specific direction for long periods of time. So it reoccurs very often, and that's why they are complaining. So basically the conclusion was that the wind is causing this reed-like vibration excitation. It's traveling through the structure and is causing the floor below to act like a speaker. Basically, like leaves down from a tree, photosynthesis that direction, except instead is the path of vibration. So then we looked at ways of fixing it. So, first the cheapest way, which is probably not going to work, but, trying it out. And that was to use vibration dampening paint to increase the stiffness of the metal sheet. It worked, but it didn't increase the performance by enough. So we went with option number 2, which is not using those neoprene pads specifically, but using neoprene isolation at the contact points for the screws. So we went with what is it called? The PB isolation, which has the double ring system in place. So that way it's isolated on each side when you thread the screws through the holes. And we also broached the idea of there being other methods to fix it, like ripping out the entire post and then reconnecting it so it's not as tightly connected, or like completely removing all of the windscreen and replacing it with a different brand. But the client obviously did not want to go with those because way more expensive. All right, so yeah, that was how I went through that entire thing. So are there any questions? That was fast. Right? Oh, sorry.
Yeah, so what method did you guys actually end up building to fix it?
So again, we started out with the paint because we were like, let's try just this one corner which has a lot of surfaces and is most likely to get excited just because it has more surfaces for the wind to excite. They said that it fixed it there. Then basically they were like, hey, but this different area now has an issue. And I'm like, did you paint that? And they were like, well, no. So then we had them paint that as well. But then we were inspecting the roof later when they were still having issues. And it's like, okay, well, these screws are coming out and it looks like you need to do more than just paint. So we went with option number 2, basically. That's what they're currently doing. So we hope that the paint would work, but it wasn't the level that they needed it to be at. So it was a visual screen, and also to let wind go through, obviously, because it's right on the peninsula, very strong winds if you're aware of the peninsula coast. So they had to block screen because of local noise ordinances, and they had to, or block site because of local noise ordinances, and they had to have it be, well, they didn't actually have to, because on 2 of their buildings, they did it that way. It was constructed that way. We were not involved in the original design.
first image you had was like a louvered one, and then
yes. So none of the pictures are actually from the project.
Oh.
I did not like specifically get permission to use images from the site. I'm just picking images of generic things like, for example, trees rather than the actual structure itself.
So it is perforated.
It is perforated. So I think one of the only pictures that is actually accurate is the perforated picture on like page 5. That one did actually come from the project, I think. Or not, maybe not, actually that might be just a generic picture. But yes, this is roughly what it looks like. It's both corrugated and perforated.
Okay.
So, were you able to experience the item sound outside and inside?
Yeah. So if you listen on the roof, it's like, okay, I hear a sound, but it's roughly as loud as the mechanical equipment on the roof. I don't see the big deal. You go down to like below, away from the windows, and you're like, wow, I can hear this. This is it. It sounds like a subway noise, and you're like, this is something. So yeah, we did experience it in both locations. Although again, on the roof, it was not that significant. Just it's transmitting through. So.
What material was the paint? Was it like epoxy?
I do not remember the specific brand. It's one of those things that you like normally apply to like trash chutes and things like that. Just like I think something like that. It's not necessarily paint. I was just genericizing. We can talk afterwards about the specific product if you want.
How effective was it? Did you measure?
They've not yet hired us back to specifically measure it. We've just been,
Gotcha.
discussing it. But if we get to the measurement point, then we'll get to it.
Okay.
So. All right.
Wonderful. Thank you.
All right. Who's next?
Who's our next presenter, Jason?
One moment, please. Next up is Sybil.
Oh,
Yay!
yay!
Good luck. I've turned it off, so you can turn it on if you want.
Yeah.
Test. Okay. All right. Thank you, everyone. I think so. I'm going to present today a case study on the Golden Gate Bridge foghorns. Not sure how many in the rooms are familiar with them and hear them. I personally was not up to this job. Yeah, hands up who hears them. So this all started, is it rolling? Yeah. Okay. This all started when a homeowner reached out to us. She's an extremely light sleeper. That was always her pitch from her to us, is that she needs, having her bedroom really, really quiet is super important to her. She was looking to move within San Francisco and was looking at 2 house options. So we helped her evaluate 2 houses. With that, we also needed to know what noise level is acceptable to her. Since her current bedroom is okay to her, we found out her average noise level and her maximum noise level. That later became our baseline about what's an acceptable noise level to her. We measured at the 2 potential houses she was looking at inside and helped her with that, evaluate and decide on the house. I know, pretty nice house. It's in Pacific Heights. It overlooks the Golden Gate Bridge, of course. And the house is, set back. She was able also strategically to locate her bedroom at the quietest corner. With the overlooking the Golden Gate Bridge, though, she came back to us and said, "Oh, but I hear the foghorns. Like, you need to help me, guys, with it. I don't want to hear the foghorns when I sleep. I'm a really light sleeper." So we were involved. We got involved in the design of it. The house is about 2.5 miles away from it. And yeah, we helped with the design, with the interior, and and also with the outdoor noise intrusion. So of course we plan to come out there to the house, do measurements when the foghorns are running, because data was not available online or publicly or in our database, and evaluate, how loud is it outside, how loud is it inside, and then what do we need to do to the facade, to the windows, to the walls to make it quiet enough to her. We also explained we cannot make it inaudible, we'll make it as quiet as possible that won't disrupt her sleep. She was receptive. We discussed that we're gonna do a presentation also to her. But okay, a little bit about the foghorns. Actually, there are 5 on the bridge, 2 at the South Pier, 3 at Midspan. They are manually controlled. They've been there since the bridge opened in 1937. And these are the ones that are at the South Pier. There's 2 bigger ones. They kind of create a 2-second low tone that repeats every 20 seconds. One faces east, one faces west. And the other ones, the 3 other ones are, let's see. Oh, I'm talking too fast. The 3 other ones at Midspan, there was no picture from them up close, but they're a little bit smaller. So 2 are facing east, 2 are facing west, 1 is facing east. They have 2 different sizes, so they're gonna make a different 2 dual-toned horn sound every 40 seconds. There's a very distinct pattern to it. It worked. So this is what they sound like, repeat it. This wasn't the measurement I did outside on the window. Here's just for reference how it kind of fluctuates throughout the year. Summer is the foggy season of San Francisco. The horns are there to guide the ships through the narrow channel between the Marin Peninsula and the San Francisco Peninsula. Even though it was summer when I planned all of this, it was still extremely difficult to actually get the measurements in. I was basically on call. I went out on site on an extremely foggy night, still didn't get any foghorns for that whole night. I was like, what's up? It's foggy out there. Well, turns out that if you don't see anything at bridge level, that's when they turn them on. But it can be that the fog is high enough where the ships have visibility to go through, but the cars don't, or the rest of San Francisco doesn't. Eventually, I was able to get measurements, as you can see, inside and outside, to be able to say, okay, what's it in the house? And here is the level. So the low-sounding horn that you heard earlier is kind of driving the whole mitigation at the end of it all. The driving frequency at 100 hertz being pretty difficult to attenuate with windows and walls. The dashed line shows the reference noise level that we're going to try to get it to for her bedroom. And then I kind of, developed recommendations, upgrades, improvements to the windows and walls to reach those goals. And in order for the owner to understand, well, what does that all mean, we invited her to our presentation studio at our office and presented 5 different scenarios to her at different levels of improvements. So here are the 3 verse ones, where you're only improving the windows, but not the exterior wall. It's kind of as a DBA hitting the level that she's okay with, but you still have that tonal character at 100 hertz, 200 hertz. You're still hearing that distinctly. So in order to reduce those tonal sounds, it was necessary to upgrade the exterior walls as well. So we then gave her 2 options, about the best one being double stud, storm window. Hey, the second best option is a sound isolation clip wall with a simple window. And here's a little graph about all those 5 different calculated options, how they compare to our reference ambient noise level. And yeah, the best option is pretty good, but the second one does fairly well. Yeah, so we oralized those 5, played them to the owner and the architect, had a lot of conversations, between what she finds acceptable to hear and the architect chiming in about what's realistic, constructability, cost, and all of that, that at the end of the day, option 2 was the one that they agreed on for the design. Yeah. The project isn't built yet. I'll be excited to see it. And I thank Diego for the help on the presentation. He helped Felipe. And any questions?
I'm fascinated that these foghorns are manually operated. Yeah.
They are manually operated.
Operating these foghorns.
Oh, yeah. I tried to. Yeah. So many things I had to lift out. Yeah. Bridge workers.
Wow.
Just Golden Gate bridge workers,
So
electricians.
24 hours a day.
Yeah.
They decide when,
Yeah.
when these things.
And they
go.
just really go by visual cue. They, at the San Francisco end, they have their little cabin, and if they don't see Marin anymore, that's when they turn them on at the base.
Wow.
And I was not able to schedule testing. There is no schedule testing. I have to really be on call.
Wow.
Like, oh, and I'm living and the funny thing is I'm living in the East Bay. I never hear them. So it's like, oh, timing. Yeah. Thank you. Any other questions? Yeah, Nick.
Did you get called out for fog? Was there
I was at the beginning I spent my time on satellite weather apps because you can see the fog there. Normal weather apps just show you clouds but not fog. And then Golden Gate Bridge camera, what do you call them? Webcams. Yeah. But they don't work when it's dark. That only helped me when it was light. So it was tricky. I mean, I went out there twice with no results that I was like, hey, I need someone in San Francisco who hears them, who then calls me and tells me they're on. I think I talked to you about this too. But yeah, one of the contractors, he lived close by and then he gave me a ring.
Awesome.
Mm-hmm. Yeah.
Did you get the whistle?
No. Mm-mm. No. Just the horns. Yeah. Yeah.
Did you do any close-up measurements of the foghorns or only at the lady's house?
No, only at the location in question. Apparently, I read in one article they're 149 decibels.
Makes sense.
Makes sense. Yeah. Yeah. Old school horns.
Until this came on.
I know.
Thing. Really can't hear them. Instruments.
Yeah, most people like them. Yeah. I mean, they have a very nice rhythm to them. And the funny thing is the rhythm is like a 20-40 second rhythm, which with the slides, I couldn't play it longer. It would take 10 slides or so. Yeah, other questions?
I guess I'm curious to know why you had to be on call rather than just running a long-term logger out there to capture the foghorns.
That's a good question. I think we just didn't want to completely be inefficient with it either. And then like when you know that they were on or not, it just seemed to make more sense to do attended measurements. Also to notice, what any distinct, have my own ears on it too. Yeah, set the level about recording threshold too. It's one thing to just measure data, but we ultimately also wanted to measure wave files. Yeah, luckily the house was empty. Yeah.
How many weeks or months did this go on? Data.
I think over the course of a month. Yeah, we started planning in June. At least it was, good chance. Last year. Wait. Yeah. Okay. who's up next?
You can buy like foghorns.
Some of the labels are funny. Be like now. Car alarm goes off in front of this one.
Right.
You're gonna measure.
Let me know when you're ready.
Okay, go ahead. All right, so my name is Shreya, and I will be talking about my work in passive acoustic monitoring of bowhead whales as they migrate across the Beaufort Sea. Also, we'll mention some of the things we found about anthropogenic noise and the impact on these whales, and then some new approaches for data analysis that we've done this year. So I work for a small business called Green Ridge Sciences. Okay. Okay, so I work for a small business called Green Ridge Sciences. They've done a lot of projects over the last many years, but the project that I'll be talking about today is their passive acoustic monitoring program in the Alaskan Arctic. They've been doing this recording, and I've been joining them for the last 25 years, and so we've got a lot of data over the last several years. So the thing that we're interested in monitoring are these bowhead whales. Bowhead whales are a type of baleen whale, which means they call at a very low frequency. And they like the Arctic waters. They like the cold. And every fall, they migrate down the Beaufort and to the Chukchi Sea, and then they'll go back up in the spring. And so we're interested in that fall migration and monitoring them during that time. So specifically what we look at is the passive acoustic monitoring. And on the left here, you see an offshore drilling island. So this is called North Star. Basically, what we're looking at is the impact of oil and gas drilling noise on these whales. So when this island was constructed in 2000, that's when they started doing this passive acoustic monitoring program. So our sensors are called DASARs. They're based on old Navy DIFAR sensors. It stands for Directional Autonomous Seafloor Acoustic Recorder. And what makes them special is they have 3 sensors, one omnidirectional pressure sensor, and then 2 vector sensors that measure particle velocity. And that is what allows us to do localization. And this is what Green Ridge does that a lot of companies don't necessarily do. So in the past and this year as well, we deployed an array of DASARs like you see on the right there. And that allows us to basically triangulate sound because we can get bearings to every whale call and use them with a lot of other DASARs to kind of see exactly where they're coming from. So on the left, all those points are whale calls that we were able to triangulate essentially. So this involves a lot of field work. So in July, right after the ice breaks up in the Arctic, we go and deploy these DASARs. We have a sensor connected to about 400 meters of ground line, and then at the end is an anchor. And we have very specific GPS points that we have preloaded before, and we go and we drop the sensor, do the ground line as well, and then drop the anchor. And then 2 months later, in late September, early October, is when we go retrieve them. And this basically involves kind of fishing for them. So we have like a grappling hook, and we go perpendicular to where that ground line is and basically just pick it up. And if it is difficult, this year in particular, we have not done this in previous years, but we used a remote operated vehicle to get one that was a little bit hard to get this year. So I can talk about that later. So this is what the manual analysts look at. Essentially, their job is to look at all of these different calls on these spectrograms and box the whale calls and then classify them. So whether that's like an upsweep or a downsweep, undulation, complex call, and they have to go through all of the data over the 2 months for every DASAR. We look at a lot of different results, a lot of different data when we're doing our data analysis. We look at things like vessel traffic, so oil and gas stuff that's up there. There's vessels taking people to and from that island. We look at broadband levels of sound, sound pressure, time series over the entire deployment period, as well as wind, because wind impacts levels of sound a lot as well. So we want to make sure we're taking that into account. And of course, we also track bowheads. So over the entire 2 months, we look at their calls per hour, and how that changes over the deployment period. We look at, for each of those calls, where it's coming from using the localization process. And then because Green Ridge has done this for the last 25 years, we can also compare that over the last several years and see how that's changing over time. So takeaways is that North Star Island, the reason this was implemented is not actually causing a lot of noise, but the vessel traffic is, especially as the Arctic gets more busy. There's also a effect called the cocktail party effect. So if you've ever been in a really noisy bar, as it gets louder, you're also going to keep talking louder. But if it gets too loud, you might just stop talking. So that's what the bowheads do too. You've kind of noticed that. So the data analysis in particular, so as you can imagine, this is a lot of data to go through. And this year especially, we deployed 19 sensors, which is a lot compared to recent years. And so we wanted to look at, is there a more automated way of analyzing these whale calls? And so hence machine learning comes to the rescue. So I devised like a 3-stage process for this. The first is detection. It's really a classification task. Basically, is this a whale call or not if I give you a spectrogram? And so for this, I use 4 classes: a whale call, noise, a disc write, and then an air gun. And this is just to kind of reduce the amount of data that is going into the second stage, which is our bounding box detection. This uses a faster RCNN architecture. And this basically does exactly what the manual analyst did, which is it draws a box around the whale call and then tells me what type of call it is. And then it also gives me actually a confidence score of, how confident is it that it is actually correct on this. And then the outputs of this then go into the third stage, which is localization. And so in this case, we have the same call, and ideally if it's the same call, it's detected on a lot of DASARs. And so we can match calls between DASARs. And so this involves some template matching essentially, and get one call from one of the DASARs and see where it matches on the another image. And then we can use the data from each of those sensors to figure out a bearing estimate. So without getting too much into the details, for the 2 stages that are the machine learning, which is stage 1 and stage 2, it's doing actually pretty well, about 97% accuracy for the that first stage. And the second stage is about 90% precision, 75 to 80% recall. So not bad and big speed up. So we'll be using that this year, actually. So future improvements, the performance depends a lot, as you can imagine, on the quality of the spectrogram. So if the SNR is pretty low, it's going to have trouble. There's also the fact that the actual box that is drawn impacts the localization estimate, just how the data is handled. So it might be possible to do a closed loop system where the localization estimate feeds back into the box detection. Maybe we can improve things that way. Some future directions, as I mentioned, the Arctic is getting a lot bigger. The ice is breaking up as it's warming. There's a lot more traffic. Shipping routes are starting to go through the Arctic. So that's definitely going to have an impact on these whales. So like the Bering Strait, for example, might be getting more busy. So this is something that I think will become increasingly important in the future. So thanks for listening. I thought I include some pictures. This at the top left, because we used a remote operated vehicle to recover one of the DASARs, is a jellyfish that we saw actually while we were there, which I didn't know jellyfish were in the Arctic. So there you go. But then we also get to see cool stuff like polar bears and Arctic foxes and caribou. So thought I'd share some of those. It is pretty beautiful up there. But yeah, happy to take any questions. Oh, good. Okay.
Do you use any kind of propagation models in your localization process?
Not any propagation models. So like, well, so basically what it uses is there's like the von Mead distribution, if you're aware. It's kind of like the normal distribution, but for circular data. And so that is helps us figure out like from a sensor where it's coming from. But basically what it ends up using is the acoustic intensity from each of those, from the particle velocity sensors in particular. So there's like one in the north-south direction, one in the east-west direction. And so we get like an acoustic intensity in a particular direction. And so that's more how the localization works. Yeah.
What is your role in this, and how do you relate to the rest of the team that's involved? That's
a good question. I'm an acoustician, but I do a lot of like the software engineering, and the machine learning is all the stuff that I've been doing. I do help with field work as well. My background is actually in like biomedical and electrical engineering, so getting into the kind of bioacoustics, ocean acoustics was new for me. But yeah, mostly all the software engineering and the machine learning and the field work. And the data analysis. It's a small company, so wherever I'm needed too. Yeah.
You said Because it's like underwater, right?
Yeah, so the wind affects the sound that is sound levels basically. So if it's a windier day, the kind of baseline sound level will actually be louder too. And so it is above water, but you know, even things above water, they'll propagate a little bit down. And so the area that we actually measure is pretty shallow. So these sensors are not made for very deep measurements. It's about 30 meters to about 100 meters deep. So you still get some noise from that gets picked up. Yeah.
Do you have any plans to put up those day stars for longer periods of time, like maybe over a year, where you have like that ice cover and there's no?
Yeah, that would be awesome. So we're limited by battery power. So we're still using the version of the Daystars from like 25 years ago. So the person who made them like incredibly robust. Like they've been doing very well over this entire period of time, but they still use like these like 60 packs of like these D-cell batteries. And so that's good for 2 months of recording. And because the ice, so we put them in right after ice breaks up, and then we pick them up right as the ice is coming back in, and we don't want to kind of we don't want to let it stay also because the ice will move it, because as I said, it's kind of shallow. And so if there have been a couple cases where we couldn't recover a sensor, just a handful over like many years, but when we do kind of recover them, sometimes like a glacier has hit it or something and it's kind of impacted a lot, or it's moved, so it's harder to know exactly where it is. And so there's kind of a couple of reasons why we want to pick it up, but it would be cool. I did ask that when I first joined too, like we should just do the spring migration too, right? So yeah.
Recording that whole time as well?
Yeah. Yes, 24 hours of data. It's continuous data from like before we set them all up and make sure the timing's right, and then throw them overboard. They're recording through all of that, and then pick them up. And after we pick them up, we unpack them and shut them down. So yeah.
Sample rate.
1,000 1 kilohertz. It's really low. Yeah.
Maybe I missed it. Who pays for the?
Yeah, so we do a lot of contract work. So this is a contract with the oil and gas company, actually, that's up there. And so they have environmental monitoring requirements. And this is part of the acoustic monitoring that they do. And actually, the people that keep them accountable are actually the indigenous tribes, the Inupiat. The whale is very important. Bowhead is very important for their subsistence hunt. And so they wanted to make sure that there was acoustic monitoring for the whales when they were trying to build this island. Yeah.
So you're measuring the whales, but the sound itself that bothers the whales is from the boats and the other equipment.
Yeah.
So is there a watchdog on that too?
So that's a good question. So it's also, what's interesting is so that what inspires the work is like, does the noise affect them? Which is kind of a hard thing if you think about it to actually measure, because how do you know if something's affected? So bowheads actually call not very often too. So if I'm understanding your question correctly, it's we know that North Star, for example, doesn't affect them too much because the sound from North Star does not propagate very far, and so we kind of we were able to say at least that this is a sound pressure level and it's dissipating fast enough. What we found with that cocktail party effect is what boatheads do is when there's vessels. So if there's like a very loud vessel, and this applies to a lot of different marine mammals, is that they'll stop vocalizing, or it affects their calling behavior. But one thing that we do is we only measure things acoustically. So it's something, it's worth figuring out, how do we actually measure their behavior in real time? Like we can see by localization whether they're pushed like further offshore, are they like getting away from the noise? And that's kind of one thing that we are able to measure, especially over time. But if we don't pick up a call, it could be that they're not there, or it could be that they're not calling. So there's some questions that are still open as to like their behavior because of anything that's happening. I hope that answered your question.
Right. They make vocalizations to communicate, but they also use it for echolocation.
So, yeah. I'm not sure that bowheads echolocate, actually. I'm aware of like tooth whales, like odontocetes. At least we don't pick up their echolocation. We pick up their calls. They're kind of very low frequency calls. Echolocation is very, very high frequency. And so the calling behavior is low frequency calls. Yeah. That's why actually our sensors are 1,000 very, very low sampling rate, but it works for the bowheads and low frequency stuff. But we actually wouldn't be able to pick up echolocation because it doesn't sample high enough to do that. Yeah.
Traffic, the sea traffic in that area changed over the 25 years.
Yeah. I can give you my best answer because I don't entirely know. I've known from what I've been seeing and hearing, I guess. I know that like when the development was happening, there was less vessels, and over the years we have been recording a lot more vessel trips. And this year they were doing some kind of construction or something like that, so that had a lot more barge trips and stuff like that we'll probably see in this year's data. But I've also heard things like there's more military exercises, or there's like cruise ships or something like that. Those are coming through more often. And so it is definitely getting busier, and you're seeing kind of more like shipping trade routes and stuff like that are going to cut through the Arctic for money or efficiency or whatever it is. So yeah, if they can, I guess. Yeah. Cool. All right, thank you.
Next.
Oh, it's working? Okay, excellent. Okay, hey everybody, my name is Max. I'm an acoustician for Resonance Acoustics, and the name of my talk today, it's complicated, but it's contactless phonograph audio reproduction. I'm going to share with you a little bit about the history of audio recording, my experience as an undergraduate researcher, and maybe the future of audio recording and audio preservation. Oh, okay. So let's start with the age-old question. If a tree falls in a forest and there's nobody there to hear it, doesn't make a sound. What do you guys think? Yeah. See, I'm not a philosopher, so I really, I'm not going to answer it for you. But I think I know somebody who might know the answer. This guy, Alexander Graham Bell, imagine he walks in, he just says, hey, look, I've invented this thing called the wax cylinder and a phonograph that can play it. We can all leave the forest and I can capture the sound of that tree falling, and I can prove that it makes a sound even when we're all not there. So yeah. So Alexander Graham Bell, Thomas Edison, and many others, they all helped invent, refine, and market the wax cylinder. It became the first widely commercially available recording product around the world. At first it was made out of wax, then a harder wax, and then celluloid, which is like a hard plastic. And that's that was a box of cylinders. These cylinders are about 4 inches long. They hold about 2 to 4 minutes of audio, and you play them by dropping a stylus on the surface, spinning them 160 rotations per minute, and translating them on their axis. Like the groove is a spiral. So yeah, cylinder records suffer from the same 4 major problems that disc records suffer from. They suffer from cracks, scratches along the surface, wear from repeated use, like from repeated playing with the stylus, and mold that will creep over the surface as they just age or from moisture. But as time has progressed, we've developed improved methods of audio recording. The digital formats that we enjoy today, they can be infinite. They can be replayed and reproduced infinitely many times without any loss of fidelity. But the problem remains that the old grooved audio formats, they're sitting in collections and they're becoming too delicate to ever play again. So this raises the question, how do we protect, or how do we get the audio from these old records without destroying them? Well, luckily somebody invented a solution to that problem. No, it's not me, but I worked for this lab called IRENE as their undergraduate researcher from 22 to 2024. IRENE, which stands for Image, Reconstruct, Erase Noise, etc. It's a lab in Berkeley. And they use a kind of scientific camera called a confocal microscope probe. They used it to scan cylinders, records, broken records, anything with a groove on it. They can use this probe Oh yeah, what the probe does is that it creates a 3D map of the grooves and how they modulate up and down and side to side. And then with a little bit of math and physics and image processing, they can recreate the audio. So boom, you've got the sound from the record without ever dropping a stylus on it. They've done some really cool things. In fact, they've recreated the oldest recording of a human voice that we know today. This gentleman here on the left, he was a French inventor, and he recorded himself singing "Au clair de la lune" on a piece of paper coated with ash, and you couldn't play it back with a stylus. It would destroy the ash, so you can scan it and get the sound back. But the main area that Irene has for improvement is for improving their model of how like a physical stylus would play through those grooves that they've imaged. If you improve the model of the stylus, you get like better audio. So that's what I worked on as an undergraduate. I would use a high-speed camera to study how the stylus would move on the cylinders to like try to understand how they respond to different stimuli. So the camera would film at 10,000 frames per second. And in the bottom right is a picture of what the stylus looks up close. It's in black and white because it films at such a high frame rate. And so you could take a picture. I could track the position of the stylus from 1/fraction of a millisecond to another, and then track the position. And then if you take the derivative of that, you get the velocity. As it turns out, the velocity of the stylus is proportional to the audio. So boom, you just get sound just from a video. It's long been thought that the cutter that creates the grooves in these cylinders goes up and down, and so all the information is stored in the vertical modulation of the grooves, and the horizontal should just be noise. However, through this camera tracking method, I found that actually, no, there is some information stored in that horizontal modulation, and what that tells us is that these old cylinders, they were cut imperfectly. The cutter came at some angle. So this is something Irene should look for, like what they should simulate their stylus at some angle to get the most information out of these records. This is something really cool. So a new undergraduate at Irene, they were looking at this 1880s disc. It was riddled with cracks. The speaker is saying something rhythmically, so they think he's speaking a poem, but even with the imaging technique, it's too noisy to understand. They can't get it. So what this guy did is that he he put the recording into this AI package called Whisper, and it created this transcription, but it doesn't really look like something that came from the 19th century. So he took that first transcription, popped it into ChatGPT, and said, hey, look for some poems from around the 19th century that fit this kind of meter, and like maybe try to find something that fits it. And it found this poem, and when you listen to the audio, it sounds, and you read it at the same time, you're like, oh my God, this is what the guy's saying. So yeah, in conclusion, scientific cameras, high-speed cameras, and artificial intelligence can help preserve old audio artifacts. Yeah, it's like not science fiction. The tools of the future will help uncover some things from the past. So yeah, thank you. And then I put up a QR code there. If you want to listen to some of the things I talked about, they're pretty noisy, so like it doesn't sound super good. Be warned. Yeah. So any questions? Yes.
How would that audio fidelity compare to an Irene reconstruction of that same record?
Okay, so the Irene probe, that kind of like confocal microscope probe, they often use it for like bio, and so it has a really like high like sampling rate. It can like it can see it gets better detail than the stylus would, so you actually get extra noise. You're getting like 200,000 kilohertz, or not 200,000, 200 kilohertz like audio. So you have to like get rid of that, and then you have to make some kind of guesswork to like get it to like figure out like the actual shape of a stylus. So it'll sound different, but pretty close after you do some noise processing. Yes.
How's the stereo coded?
How's the stereo coded?
Yeah, how is it with a single stylus?
Yeah.
How does it encode stereo?
So stereo is usually encoded with it's called like the 45-45 method. So like on like a disc record, the left wall will be your left audio channel, and the right wall of the groove is your right audio channel. So the two sides of the grooves modulate differently. So you get a stereo, like you get two recordings in one groove pretty much. The old cylinder records, they were just there was only mono. So yeah, that was a pretty clever trick to like get it one. So now when you drop a stylus on your record, you have like two pickups that are orthogonal to each other basically. And so one pickup will just measure one wall of the groove and the other one will measure the other, and there's no little crosstalk pretty much. Yes.
Did the shape of the stylus change over time?
Oh yeah, it did. I think they got bigger, smaller. They changed a lot. I was messing with different sizes of styluses too, because the grooves would change shape too. So like on the cylinders, the grooves were a lot shallower and smaller, but on vinyl they got a little deeper. And yeah, when they invented stereo, they had styluses that were good for the measure or picking up the two walls of the grooves.
Did you come across any approaches for scratch discs?
I didn't get to study like noise, how styluses like respond to scratches and stuff, but that's something you could do theoretically, like film it playing a bunch, like a stylus playing over a bunch of scratches and like seeing how it jumps or something. And if you wanted to, you could be like, okay, like Irene scans a cylinder or a record, sees a scratch, but like maybe they want to put in that nice like vinyl like crackling and popping if you wanted to, like if you could model that. Yeah, so something it could do. Hasn't been done yet, but anyone else? Okay, cool. Thank you very much.
Okay. There we go. All right, yeah, let's do it. All right. Hello, everyone. My name is Spencer. I'm an acoustician with Resonance Acoustics. And today, my presentation is going to be focusing on artificial intelligence and some of the ways that we can leverage it in acoustics. So I'm going to start off with some general information about AI and then get more specific about how we can apply this in acoustic-specific use. So AI is really a broad category with several subcategories. We can go into machine learning, which focuses on pattern recognition, getting into deep learning, generative AI, and large language models, which can produce human language in response to a prompt. Now, going down the tiers here, we get into kind of different applications of AI. So here's some that probably everyone's a bit familiar with. Of course, this has been growing a lot in the past few years and becoming very prominent. Some services like ChatGPT, Gemini, Copilot, DeepSeek, all ones that we're pretty familiar with that focus on having chatbots. And one thing that all these products have in common is that they use large language models, or LLMs. So these models are trained on massive sets of data that can allow it to become very efficient at pattern recognition and produce intelligent responses. The responses can be adapted to be tailored to specific applications as well, which we've probably seen some evidence of for those of us who have kind of explored some of these chatbots. So going into one of the big ones, ChatGPT, right here, we just see some of the most common uses for it. Of course, very wide variety, getting into programming, summarizing documents, even getting into conducting research or handling customer service. So these are some uses that can be applied in kind of a general business sense. And here are some that are a bit more well integrated with specific programs. For example, Copilot, which kind of speaks to Outlook and the Microsoft Suite. Otter, which can look into your meetings and create summaries. And Gemini, which works well with the Google suite of products and Gmail. Now, that's great and everything, but let's start to get into how this can really be used in AEC and the built environment. Now, we just talked about our great uses for it, kind of that can be applied to a wide range of categories. But for acoustics specifically, we can kind of narrow down a little bit more and really get into the weeds of it. So some applications can include creating programs with it, something that many people are not necessarily proficient with in our field, but this can turn you into an expert coder. Not really. But creating marketing proposals, getting into finding city ordinances, legal documents, or enhancing the efficiency of spreadsheet commands. Now, in acoustics, we can go into a bunch of different fields from here. We can talk about the architectural acoustic side of things, environmental, getting into even material design, material placement in different spaces, noise monitoring. So now we're going to get into some more specific products for AI into acoustics. So one thing that we run into a lot is environmental noise monitoring, where you might have a long-term meter, but your microphone is picking up various extraneous sources, which might not be what you're necessarily interested in. That can lead to kind of some extraneous results in your data set that you're capturing, and a need to filter through those to just try to detect what's going on, which can be a time-consuming task. Now, there are some products such as Sventech and Rizzo, which can look into your measurements and actually classify different sound sources based on its learning algorithms. So let's say that you are trying to measure a construction site and you get a pedestrian nearby that's yelling and everything. Well, now this makes it easy for you. It tells you what's going on that time. Room acoustics is another one. So a lot of times we will create models of different spaces to try to understand the sound distribution, reverberation in different spaces. And the problem becomes that a lot of iterations of these models can come about, which can be time-consuming and inefficient. Now, one product we have is Ready Acoustics. This is one that can create thousands of iterations of a given space to try to optimize room geometry or speaker placement. Can make recommendations for sound-absorbing material placement or diffusion, which can save a lot of time in the workflow of things. One other interesting one is dynamic surfaces. So when you're designing a space that has multiple uses for variable acoustics, this study actually looked at fitting a room with multiple sensors throughout the space to detect what the use is at a given time. And it can create these dynamic patterns to optimize room acoustics for a given use. For example, for a music performance, it will make more reflective surfaces, or a lecture will expose more absorptive cavities. Active noise control is another one. So you can use a series of microphones with an AI algorithm to make more intelligent decisions about sound cancellation, whether that's in headphones, or there have also been studies that have looked at this for environmental noise intrusion, creating sound masking in a space. Even safety management for construction sites is something that AI can be applied in. For example, you may have a very busy and noisy construction site where safety hazards may be a concern. So this can actually look at, is being used for collision detection and can alert the workers of issues, and that looked at a more cost-effective solution to achieve that. Predictive maintenance, another one, especially in factories, something that has a lot of transformers, turbines. When that equipment is down, they lose money. And these devices, Zeno, focuses on using different sensors to actually recognize different patterns that these equipments can produce to alert people to maintenance before the equipment actually goes down. Now, a big concern with using any kind of AI is privacy at this point. All of that data is being sent back to the product servers to kind of enhance their products. So we need to be aware of that, especially when dealing with confidential projects. Also, AI is not perfect, especially in this day and age, even though there are being many advancements. Hallucinations are common, which is when an AI will produce a factually incorrect result or could contradict itself. So it's really important not to rely on AI as a catch-all and kind of be aware of what you're putting in there and what it's putting out. So at this point in time, we're in a very exciting time, honestly, because AI is making leaps and bounds every month. But the key at this point is to really use it as a tool to try to increase efficiency, help with given workflows, and not trust it implicitly. Being aware of the responses that's given, fact checking them, and yeah, thank you. Yeah, happy to answer any questions or open it up to discussion. Love to hear how everyone has been using AI in their daily work.
Applications, would the AI be used to, like if you're doing like spectral analysis of like the space or something, would it be used to actually do the work of modeling that? Versus like using like FEM software or something instead, or is it purely used for going through like the iterations of like how do you arrange the space?
Yeah, so I think that it's definitely more on the latter of what you said, creating different iterations. So you have a given space, given model, you have some desirable criteria, performance targets, and you can feed it to that in a variety with different options to achieve that.
Have you, going back to the environmental noise element of like doing the sound analysis of like, hey, you might take that out. Have you worked with those programs before, and how effective are they?
Yeah. Unfortunately, I've not gotten my hands on too many of these acoustic specific products. A lot of them are, expensive monthly fees, which we have not integrated in our workflow quite yet. So I'd love to check that out and kind of see how it stacks up. But I have heard positive things about it. It does seem to be relatively accurate from the reviews that I have read. I'm sure that's not perfect, like anything.
Yeah, that makes sense. I'm curious if you had any firsthand experience.
Yeah, absolutely.
Yeah.
Do you have any that's just asking you to make acoustical recommendations for you on a project?
Asking for a friend.
Yeah, great question. I feel like in those cases, you're almost need to spoon feed it, kind of really push it in the right direction, giving it a very detailed prompt to, put something out that's can actually work for the project. I think it's one of the big limitations with AI right now in our field is that it really does not, have all the design considerations baked into it or understand what the design intent might be from the architect or what potential limitations may be unless you're telling it explicitly. And even so, it may produce something that's not actually feasible for your project.
AI told me that this is what you have to do for acoustics, and it wasn't correct. But so he had to try to convince the client that it's great you got that from AI, but you can try it if you want, or you can listen to what I'm saying, but it's up to you.
Yeah, I happen to have ChatGPT on my phone, and so when they asked me that, I asked the same question, and I got a completely different response or answer. And at the very bottom, and this is something that they do because they don't want to put any liability on themselves, they'll say, please contact an acoustical expert because they know more than I do, which is great for us, right, in terms of our job security. But yeah, I did find it interesting that like for the same prompt, it gave us two different responses.
Yeah.
So that's what I was like, you can't really trust it.
You asked two acousticians, don't you?
Yeah. Yeah, I'm talking to a person rather than like a computer, right? You're just like, yeah.
Yeah, it's interesting. And so some of these chatbots can, if you look like logging to account, will kind of create a profile of you almost, going back to the whole privacy concerns, understand what kind of details you're looking for in their responses and try to tailor it to you. And sometimes it gets over tailored to the point that's like, this is not objective anymore.
Right.
I'd just like to chime in and say, definitely the code search seems like a useful thing. Like earlier today, I was searching for like San Gabriel, California, ordinance stuff in it, and ChatGPT gave me like 3 links to San Gabriel, And then one linked to like Google Hide. It gave me useful links.
Yeah, that's great. That's a great point. Also, you bring up something that can be useful, in fact checking ChatGPT is to ask it to, provide its sources so that you can actually verify that this is real and it's not just coming out of nowhere.
Just another experience. I had a contractor submit an RFI the other day with a screenshot from ChatGPT that said what they wanted to do was STC 56. Get ready, those are coming.
Was it STC 56?
No.
So I'm curious, like, with all the architectural physics academicians in the room, is there anything that you feel like you've gotten over many years of experience that you feel like AI has been completely like doesn't pick up on at all? Like that there's like a feel for something and anything in particular?
Yeah. At least, I'll start, I guess. I think that, sorry, it totally depends on the application about how far off it may be. But let's say that you're looking at room acoustics applications and you're trying to figure out saying, hey, these are the dimensions of my space. Can you tell me what the reverberation time may be? And the more you try to get into detail of that, getting into quantitative metrics from it, the more it seems to struggle, at least in my experience. It might be able to give you, a nice little, oh yeah, it's gonna be pretty echoey or it's not gonna be, but not getting into specifics.
Also, a lot of the data is behind paywalls like Plytech, et cetera. Like the companies will have to sign in specifically, so the AI systems, maybe I'm mistaken, but a lot of them probably just don't have the actual data incorporated within. So it's whatever you can Google online, which is not always good.
So one of the things is we tell people in our company, please don't submit your whole report to AI to proofread it or make it sound better, because that's how it's starting to collect information, but it doesn't understand the context of the recommendation. And that's where, two academics sit in a room, you ask them what the problem is. There's a context there to discuss. And so that's what's missing. We have various levels of experience, and some have had that one room where it's like, oh, that happened there. And someone else may not have had that. And so some of the rooms are like, oh, says you do this. Or the kid right out of college says, my textbook told me this is how I have to calculate stuff. We've all had the kid out of college who came with the acoustical degree, no offense to anyone here who has one, and they walk in, they're like, it tells you I need 5 layers of concrete floors in order to meet the right thing. It's like, no one's gonna build that. So it's that sort of things that it's missing right now. That if you just take it for what comes out of it right away, you have to be able to check it and see if it's right or not. And most of the time it's not.
Well, my question was going to be towards you because you asked that question to us, because you said you use it for your learning, right? You do some level of. How effective has it been in your experience?
Yeah, so I don't use any LLMs for that. Which I think so I use a classifier and then the bounding box detection. So those are very specific tasks that I have to depend on the training data and have a lot of data, but for many years of recording, but data quality is still an issue. Yeah, LLMs, I think I'm not really using any LLMs for my work. Well, just like, now and then I'll kind of ask ChatGPT like help out, but with coding or with like quantitative stuff, as you said, it's definitely not right all the time. And you kind of have to like ask questions very specifically or kind of have it, help your own thought process more than really take it what it says, I guess.
One other thing real fast is just like AI has encompassed automation. We've been doing automation for a long time. The AI in Revit is actually just automation. Hey, I don't need to draw every single tile on a bathroom wall anymore. Architects go, give me a wall and it's like that. I want a subway tile. Okay, and it ships it. And so it's automation that's helping out. That's the higher level of stuff. You've had it in Word where it's like you start typing it's like, oh, I think you want to say this. And you've noticed that it's not always correct. You go like, no, actually, I want this word. It starts learning from what you're typing. So it goes, oh, you're trying to say that again. That's not exactly correct. And that's all it's doing as it's learning. Because it doesn't know what a DB is until you type it enough. And then it goes, oh, you must be saying DB. So that's the learning portion of it too. So it's, separating the automation from the AI, which is like the learning of like, I just heard this, that is a bird, that is a person, that is this. That's the AI portion of it, just pulling from all these sources. Like it statistically says it's a bird, so therefore this is a bird. So you don't have to, do anything with that. Versus just, can you do all my 500 calculations for me? We've had programs that can do that for a long time. Just not all of them. So
it's pretty decent at if you know how to describe a bunch of things kind of dancing around a certain term. Like sometimes at like 4 p.m. you're trying to get a report out. You're like, what's the word for that? What, you can't remember what a dormer window. Some niche architectural term. You just type in what's the name of the window that goes above the other thing that's next to the other thing, and it's usually pretty good at saying, oh, this is probably what you mean. So like for a quick task of like you just have like word finding issues or something. I don't think that's worth $20 a month, but it has come in handy every once in a while.
Yeah, definitely. I've had similar experience with that. I think that like, more basic tasks like that, like, oh, is my grammar okay here? Or what's this word supposed to be? It's pretty good that, and it's been getting better every year. All right.
not least, Matt.
Oh yeah. Hello, everybody. I'm the last of the 3 Resonance Acoustics amigos. My name is Matthew Christian, and today I'm going to be talking about something that we do not at all do at Resonance Acoustics, but is instead the topic of my master's degree research. So I was a master's degree student at Brigham Young University from 2021 to 2023, and I studied under this man here, Kent Gee. And Kent, his research focus is specifically on supersonic jet noise, specifically from afterburning military aircraft and from rockets. You can see there in the middle, that's the only picture I could find of myself presenting during my entire master's degree. So folks, remember to take pictures of yourself. But the research that I focused on specifically was on the T-7A Red Hawk, which is a new supersonic jet aircraft trainer for the Air Force. You can see the top picture, there's a panoramic that shows all of the microphones that we used in our measurement. And during the measurement, we ran the aircraft from idle to full afterburner 6 different times. So we're talking about a ton of data. My research specifically focused on our far field arrays, specifically at 38 and 76 meters, 125 and 250 feet for those of us who don't speak metric. And these microphones were arranged from 30 to 160 degrees. The goal of my research was to take this data and reconnect supersonic jet noise study back to its acoustical roots, using this data to come up with simple, basic acoustical parameters. So for example, we can look at our directivity curves, and you can see going from 50% thrust to full afterburner, how much louder it gets, and how the peak radiation angle moves further and further up, right, from 160 degrees back towards like 110 degrees. And beyond just looking at our overall sound pressure level spectra or sound level directivity curves, we also look at the frequency dependent directivity curves. And we see funky things like there's a fun little double low pattern at the 315 hertz frequency. This is all narrowband, by the way. And we can see how at low frequencies, there's a lot less noise, and the noise tends to get more and more tonal. These are the spatiospectral maps that we created, where the x-axis is the degrees, y-axis is frequency, and the color represents the overall level. And you can see right here, we started to notice there are these holes that started to appear in the spectra that couldn't be, well, initially we couldn't explain. And we realized that these microphones that were mounted about 5 feet above the ground were dealing with a lot of ground reflection interference. So we used a model that accounts for both a finite impedance ground and a turbulent atmosphere to create this ground reflection correction spectrum that we could use to essentially subtract from the original raw data and create this essentially free field corrected data of our aircraft measurement. This is the first time this kind of model had been implemented in this kind of study. So you can see the black curve shows what was initially recorded, and you can see a very obvious null, roughly at 700 hertz. That was from the ground reflection, from ground reflections. And once we implemented our model, we got a much more smooth curve that would be expected based on our near field measurements. Here you can see at all 4 of the engine powers that we measured, the effects on the overall sound pressure level. And you can see it's not huge, but it's not nothing. And accounting for these ground reflections will change the different parameters that we're measuring from these aircraft. And again, the first time this had ever been implemented on a full-scale aircraft study, something I was very excited to do. When we corrected our spatial spectral maps, you can see now, again, the holes that had existed before, right around here, are now gone. So it's not a perfect model, but it's a good first step as we try to correct for these ground reflections and more approximate a free field measurement of supersonic aircraft noise. Now, with this free field data, the next step we wanted to take was to create or to calculate the sound power from the aircraft. So very simply, we did a basic numerical integration where we took the sound intensity measured at each of the far field microphones, took the product of that and basically the spherical strip, assuming it's axisymmetric, and we came up with an approximation for what the overall sound power of the aircraft would be. And we wanted to compare that against the mechanical power of the aircraft. So we had an idea of all the power that's being put through the jet, how much of that energy is being turned into noise, acoustic efficiency. Lower values mean that it's creating less noise, higher value, more noise. So ideally, you'd want as low of an acoustic efficiency as possible. And this is something that was studied historically in like the earliest jet noise literature. And they found that for subsonic jets, the sound power increased proportional to the jet velocity raised to the 8th power. So huge jumps with just small increases in velocity. And then for supersonic jets, it increased relative to the velocity raised to the 3rd power. I know this is going so fast. But what we're looking at here, this steep line, that's the 8th power curve, and this is the 3rd power curve. Our subsonic data points matched almost perfectly with the 8th power curve, and our supersonic data points matched almost exactly with the 3rd power curve. And so we saw an agreement with classical jet noise literature with our ground reflection corrected model. We also compared what we saw with classical rocket noise literature, where you can see the gray points were rocket noise data points collected in the 60s and 70s. And what we saw with this jet trainer is it fits right along with those rocket noise data points. And we can see the acoustic efficiency varied from about 0.2% to just a little bit below 1%. So the last thing we wanted to look at was the directivity indices of the aircraft at different aircraft conditions. So directivity index, right? Very simply, right, we have 2 curves, equal sound power. The blue one is the jet noise curve, and the black one is from a simple source, omnidirectional. The directivity index is just the difference of those 2 curves. And so we can see how directional or how much directivity the noise from the jet has. And we saw that as it got higher and higher, right, from 50% to afterburner, it got less directional. And again, we can see the peak radiation angle moving further and further aft, and that lobe widening. So this research that I was fortunate enough to be a part of was, again, the first implementation of a ground reflection correction model in supersonic jet noise. And it was an attempt to reconnect jet noise studies with its classical roots by implementing parameters such as acoustic efficiency and sound power, things that aren't really discussed in contemporary jet noise studies. And so in the future, especially as we're trying to develop technologies that make jet engines more and more quiet, we don't want to sacrifice performance. And so acoustic efficiency is something that's critical in how determining which ways of making jets quieter are most effective. Anyway, that is the end of my presentation. I'm happy to take any questions. Dennis?
You ever get to ride?
I wish. One day, maybe. It's a dream of mine. If any of you own a jet engine aircraft, give me a call.
Sold mine recently.
Oh,
So it seems like, towards the afterburner side, it was almost like 120 degrees was where the most directivity was coming from. Like, is there some mechanism shooting sound at that angles, or is it like still going behind and it somehow is more, 120 degrees rather than like 180?
Yeah, excellent question. So we saw that that like 120 degree directivity that came specifically from Mach wave radiation. So as you had these coherent structures that formed in the jet stream, essentially you have these like large pockets of air that are moving at supersonic speeds, and the Mach waves that come off of those coherent structures are what caused those 120 degree directivity bump that we saw.
Reflection. Did you just one day someone walked in, it's like, I bet you it's the ground, or did you do some vertical measurements and like high low to see if it disappeared or any of that sort, like, or move it like 2 feet and see if it moved in frequency?
Yeah, so it was something that was well known. I mean, we were mounting the microphones 5 feet above the ground, like on pavement, so we knew that ground reflections were going to be an issue. It was actually a model that Ken had developed earlier for a completely different study. But to answer your question, no, we didn't have the opportunity to do those different kind of studies. It would have been cool to have done that.
But you pulled from older research, which said that's what it is, and that's how you.
Exactly.
What's your sense of what happens from subsonic to supersonic to make it go from a cubic to the 8?
That's a really good question. Can we actually pull up that figure that shows all 4 engine conditions? Because it's something that is currently unexplained. You can. Yeah. So especially we want to look at this jump from 75% thrust to mil, which is kind of like the standard military power. There's a huge jump in sound power there that doesn't follow either of these curves. That is, at the moment, as far as I'm aware, completely unexplained in jet noise literature. So long story short, I have no idea.
Anything in your education that was transferable to what you're doing now, or how did you go from doing that to acoustics, building acoustics?
That's a great question. When I interviewed with Randy, I tried to convince him that this would be very transferable, and he was right in telling me that it wouldn't be. But ultimately, I think what this research did help me understand is because we wanted to connect these jet noise phenomena with classical acoustic characteristics like sound power, directivity indices, etc. It helped me have a really solid acoustic foundation that I could then use to better understand like architectural acoustics, for example.
Did you ever explain any of this? Do a presentation?
Oh, frequently.
Language?
Not necessarily to lay people. So I got involved with multiple ASA presentations and got to present at like AIAA conferences. And those were honestly extremely helpful. I'm glad you actually brought that up. I hadn't even thought about that. But that was something that's been hugely important in my professional career. But not with a non-acoustics or non-engineering type audience, no. I don't know if a non-engineering or acoustics type audience could stay awake for this kind of presentation, to be honest, but.
I would say never about the jet assessment, because we worked on projects where we're looking at the effect of jet noise inside residences.
Oh, cool.
Yeah, so that project that we're sort of in we've had dabble in a few of them. So like I said, never say never.
Cool. Very cool.
Yeah.
Oh yeah.
I'm just curious where a commercial airline falls on that group.
Like way down. It's very, very subsonic. So very much in the the 8th power regime.
So I wasn't quite sure. So is the plane actually moving, or is it just shooting off it?
Yeah, also a great question. Sorry, we can go back to the panoramic picture. This is called the jet run-up pad, and you can see you have this like curved. Answer's short. It's stationary. We had it uniquely pointed away from the jet blast deflector, so we had a very preserved jet downstream, which is something that was also very unique about this study.
The jet's not moving, like the afterburner.
Right. Oh, so the aircraft's not moving. Technically, the jet is the air that's being injected, and that is moving, but that's being a little bit nitpicky. Well, yeah. Yes, exactly. Yeah, for real. Yeah, we didn't want to have like a Looney Tunes style takeoff where it ran up that ramp.
Get any different directivity when the plane's actually moving? Like you were talking about coherence and stuff earlier. Is there any effect on that? And does that shift like where the lobes are?
Yeah, I'm sure it is. It's hard to get acoustic measurements of moving jet aircraft, but I can tell you the same research group, Kent was really involved. I know, especially the last couple of years, he's been super active in measuring rocket noise, and they've developed some algorithms to basically like account for the directivity as the rocket's moving. And the directivity they're seeing from those rockets, it matches the theory that with what we're seeing with this stationary aircraft. Any other questions? Okay, yeah.
So, the directivity changes to be more wide as the sound goes up. Just wondering, does the sound actually ever drop like on the 150, or is it just like dwarfed by the now extra sound at 120?
It's more that, yeah. So all the sound mechanisms that exist in the subsonic regime still exist, and they're getting louder. But with with supersonic flow, you're getting way more noise that's gonna, yeah, like you said, dwarf every other sound source. Yeah. Mm-hmm.
Is that just the sound of the supersonic like path in mind, or?
Yeah, okay, so the way you can think of a sonic boom is, so you have aircraft moving at a supersonic speed, right? And it's compressing the air in front of it. Because it's moving faster than the air is able to transmit that pressure information, you get basically a cone of a pressure wave that propagates both above and below the aircraft. And the sonic boom is what happens when that cone passes over the ground over a receiver and you experience that shock wave. Yeah, I don't know. That's my basic explanation. I have a room full of professional acousticians, so I'm a little bit nervous. Did I do well? Yeah, no, that's how I best. Does that make sense? That's how I best understand it. Yeah. I'm not a sonic boom expert, unfortunately. Great. Okay. Thank you very much.
I just wanted to say thank you to all our presenters. I think that was amazing, and I think we all had a really interesting evening. So thank you very much. I know it's not easy to do these things on the weekends and the evenings, and I really appreciate all your work for our community.
Before we stop, thank Christina for this great idea, because she said, we should do this. She saw it somewhere else, so she's like, we should do this here. So yeah, the LA chapter did it before us. If any of you all have an idea for the event, please let us know. We're always looking for ideas. I thought there was a hand wave. I was kidding.
Nathan's like, maybe.
Thanks, everyone.